Do you hear that little voice? I hate her little voice.
Hang
on.
We'll like it. Good.
Okay, I'm just gonna let anybody come in. Let people just drift in rather than have to do that. Okay, right.
Ready.
Hello. Hello, Genesis. Hello, Genesis. Ah, they're awake. Good. Excellent. Well done. Hello, Silver Spring. You guys are just too cool, aren't you? Yes, I know. Okay. So last time, which was weeks ago now, we were doing mole calculations. Now, I said we will take a break. We will stop doing moles and we will do something different. And what we are doing today and next week is about energy in chemistry. So it's about exothermic, endothermic, energy profiles, all that sort of thing. So that's what we're going to do, okay? It has some calculations. They're not terribly difficult. I'm going to show you the pattern of what we will be doing over the next 2-3 weeks, depending on how it goes. Some of this is from Form 2, some of it from Form 3, and some of it from Form 4, okay? So it's all about energy all the way through, okay? So hopefully everybody can see. I must say that Genesis has got very nice, just about everybody's in green jumpers, but we got one red jumper. Is she the head girl or something? Oh, I have to put this behind me. Okay, so I'm going to show you what we're going to do. So if you want to write stuff down, that's okay. But I am going to record this. I will put it, I then will send to the supervisors a link to YouTube. So you can see it again if you want. If you want to write stuff down, write it down, okay? But the questions you will be sent so you can look at them afterwards. I'm going to just show you what's happening. Michael, are you okay there? Can people hear? Okay, that's good. Okay, and Silver Spring, you can hear, yes? I hope. That's excellent. Well done. Thank you very much. Okay, so what we're going to do is I'm going to share my screen. I'm going to show you what, I hope I will show you what it is all about. I hope you can see this, which is the overall pattern of what we're doing. Okay, this is what energy is all about. There's no need to write all this down, but this is showing you where we will be going. So it starts on number 1, goes round 2, 3, 4, 5. Number 5, the practicals, is where we will finish, and we will actually be doing, I will be showing you how to do practicals and measure things and so on, okay? Hello? Are we okay, guys? Yep. Right, I hope everybody can see this picture. Can you see this picture? Yes? Guys at Genesis, okay, good, excellent. So we're going to start top right. And today we're going to do number 1, number 2, okay? We're not going to go any further than number 1, number 2. And we're going to start talking about energy and exothermic and endothermic. And it's very important that we know the terms, the words that we have to know, okay? So we've got to know about exothermic, endothermic. We have to know about delta H. We know how to be able to recognize changes of state and what that tells us about the strength of the bonds. And then we will be looking at energy profile diagrams as well, okay? So this is what we're going to cover at first. After we have done that, we will move to bond energies or bond enthalpies and breaking and making bonds, and something that I use, which I hope will make life easier, which is called bendomexo, okay? So that's what we're going to be looking at. That's just number 1, and number 2 is what we're going to be looking at today. Okay, so that's where we're going to start. So I want to know, we're going to use a thumb up and down and so on. Are you okay with exothermic exothermic and endothermic. Do you know what exothermic, endothermic means? Oh, Glory. Hello, Glory. How good to see you. Okay, Silver Spring, no. Genesis, yes, no. Exothermic, endothermic. Are we okay or not okay? We're okay. Glory. We are talking about energy. Are you okay with exothermic and endothermic, the meanings of these words or not? Okay, not okay. You're okay. All right, we'll look at those. Are you familiar with delta H, the triangle and the capital H? Genesis, are you familiar with delta H? Okay. Silver Spring, have you not heard of delta H? Okay. And Glory, delta H? Excellent. That's okay. So if I wrote a delta H, could you tell me if it was exothermic or endothermic? I'm going to tell you a value, okay? I'm going to, I will share my screen and I will write it so you can see it. Okay, so here we go. So if I go on this screen here and I write, sorry, I've just got to change my angle. If I write delta H equals -890 kilojoules per mole. Is this exothermic or endothermic? If it is delta H is -890 kilojoules per mole, does that tell me it's exothermic or endothermic? Exothermic or endothermic? Let's see who knows. So we're going to go for exothermic or endothermic. Okay, exo, endo, it's -890 kilojoules per mole. So Genesis, exo or endo? Yeah, you're right. Okay, all right. Silver Spring, exo, endo, or if you show me this, it shows me you don't know today. Okay, exothermic. Glory, what do you think? Gloria thinking exothermic. Okay, all right. So what we're going to do is we're going to go, we'll go back a stage and I'll show you what exothermic, endothermic, and delta H means. So you can write it down if you want to. It's important that you're really, really familiar with these ideas. Okay. So here we are. I'm going to introduce it. I will draw you an energy profile that hopefully will explain what it's about. Okay. And then I will ask you to do one. So I'm going to go back and I'm going to share my screen again because it's the easiest way to show it. Okay. So if I talk about energy and it goes up. So this is high energy and this is low energy. And if I watch a reaction, so I have time along the bottom, and I am going to think about a reaction like fire. Okay, so I'm going to look at fire. So I'm going to burn some carbon. Now, when I burn carbon, what I have is I have carbon. Carbon is just charcoal. So carbon and oxygen makes carbon dioxide. Now, when carbon and oxygen combine to make carbon dioxide, it follows a pattern like this. So if the energy of carbon and oxygen is here, carbon dioxide is lower energy later on, so it has burned, it is down here. So carbon dioxide is down here. What happens between these two is the graph goes like this. It starts here and it goes up and then it goes down to there. This here, this having to put energy in, this is matches. or a lighter, something to make the fire start. Okay, so this is starting the reaction. Okay, so I'll just get rid of that because that's out of the way now. Okay, this is here, this energy here is called something. Does anybody know what this is called? Anybody at Genesis, do you know what this energy, where I have to put it from here up to the top of here, we call this something? Anybody at Glory? Anybody at Silver Spring? Have you got anybody there, Fiona? Have you got anybody, Michael? Have you got anybody, Dan, who knows what this is called? I could see one there. Let me just stop sharing just for a minute. Let's see if anybody can tell me what it is called. What is that peak called? The amount of energy we have to put in to start a reaction. What do we call that energy? Can somebody show me? Or tell me? Say again. Sorry, I can't hear you properly. I'll have to turn my, hang on, let me turn my speaker up properly. Mine is very quiet. Hang on. I'm afraid I'm glad that it entertained your team there in Glory, but I can't. Your mute, your sound is very quiet. Anyway, it doesn't matter. It is called the energy. Oh, hello. You're going to try and show me it written? Ah, hang on. Yes, thank you. Yes, well done. Very good. It's called activation energy. So back to the picture. So back to the picture. Here we are. This is called energy of activation. And it is the minimum energy that the particles need to react. Okay. So it's the minimum, and this is a very important idea, minimum energy the particles need before they can react. Now, that's important because it's before they can react, okay? It's before they can react. The minimum energy that the particles need before they can react. When they react, they need to crash into each other. They need to collide, okay? But this is the energy which they need before any collision can lead to reaction. If I am driving a car and I crash into somebody else, then the amount of damage which I get, the amount of damage which is caused to the car depends on the force crashing. If you are driving a car and you just gently hit each other, there is no damage. If you hit hard, there is much damage. Molecules, particles, atoms, when they crash into each other, they have to break. They have to break so they can make a new chemical, okay? And this is breaking bonds. It's a very important idea. Now, so that energy, if they don't have the energy of activation, what they do is they hit each other and they just bounce off. Boom, nothing happens. If they hit hard enough, then they can break and form a new molecule. This is a very important idea. Energy of activation, the minimum energy they need before any collision can work. Okay, that's really important. So back to the diagram. Now, if we go back to this diagram here, if I look at the energy difference between, no, let's go red. Between this where we start, the level where we start, and the level where we finish, there's a drop in energy. And that energy is going to be given out. If I drop something, I know that I hear it hit the floor. I see it roll. I see it maybe smash. In other words, we know that when we go down from higher energy to lower energy, we know energy is given out. This is energy given out, or what we call lost. Okay, given out or lost. And that's a really important idea. If the starting is higher than the ending, in other words, it's going down in energy from here to here, then energy is lost. Okay. Now, what that means is that then I can say, okay, if I have carbon and oxygen and it turns into carbon dioxide, then we write delta. This is a Greek letter. It is delta. Okay, it's like a capital D in Greek. H, this is heat. Delta H is negative. And it's 393, and it's always measured in kilojoules per mole. In other words, if I burn 1 mole of carbon, I get 393 kilojoules out. And the key thing is this. This here, negative, is lost, is exothermic. Negative is lost, that is exothermic. Okay. So hopefully that makes a little bit of sense. So we've got the diagram there. Let's just shrink it down a little bit. There it is. And hopefully this will make sense now. Okay. Okay. Okay, so does anybody have any questions about that so far? Anybody have any problems with that idea so far? So delta H means change in heat, change in energy. So you are today sitting there, you are giving off heat. You are an exothermic reaction happening. When you eat food, your food is digested and some of it heats you up because it is an exothermic process. But there are some reactions which are endothermic. Endo means it takes heat in. So if you have a reaction which takes heat in, then it will absorb heat and it won't get any hotter. It will get colder. Okay. So we're going to write that down because that's quite important. But exothermic means if the reaction is exothermic, it gives out heat. If it's endothermic, it takes in heat. They're very important ideas. And we're going to give a couple of examples of each one of them, okay? And then we're going to have a look at a question. So here we go. Okay. All right. So exothermic is heat is given out. And delta H is negative. Endothermic, is heat is taken in. And delta H is positive. Okay, that's important. Now, it is always true that for both of these, it doesn't matter which one we're talking about, delta H is change in energy. And it's measured in kilojoules, whoops, per mole. That looks like kibo. That's kJ/mole. Oh, okay. Thank you. That's a shame if I haven't projected that. I will come back to it. Hang on. I will share it again. Okay, here it is. Exothermic is heat is given out. Okay, it is always about things getting hotter. So exothermic is about heat is given out. So things get hotter. But endothermic, whoops. I don't know. Endothermic is heat is taken in. And delta H is positive. Both of them is delta H. And delta H is the change in energy. And it's always measured. I'm sorry, my handwriting here was rubbish. I will just get rid of that and I will write it again. It's measured in kilojoules per mole, which is written small k, capital J / MOL. Okay, it's always in kilojoules per mole. Okay. Okay. So we've got exothermic, we've got endothermic. We have seen this diagram with the what we call energy profile, which I'm going to look at again in just a moment. And now we are going to move on a little bit. Okay, so here we go. So I'm now going to look at two different reactions. In the two reactions, I have CH4 plus 2O2 goes to CO2 and to H2O. Can anybody tell me what CH4 is? Can anybody shout out and tell me what CH4 is?
CH4 methane.
It is methane. Thank you. It is methane. And when it burns, it gives out heat. So it will be minus 890 kJ per mole. Okay. So CH4 plus 2O2 goes to CO2 plus 2H2O. So it's forming carbon dioxide and water. And this is the value for the delta H. Now, if we want to draw this as an energy profile, I'm going to give you a chance to do it first. What I want you to do at first, excuse me, is I want you to try to draw a diagram like we did before. I'm going to show you the beginning of it. So we're going to start, and it's going to be like this. So we're going to have energy up the side, and along the bottom, we're going to have time. And here, we're going to have CH4 plus 2O2. What I'd like you to do now is to try and work out what the rest of the diagram is going to look like. The energy of activation, you can't know the number, but you just have to look at it and just go, okay, well, it'll be a peak. The question is the carbon dioxide and water here, where is this on this diagram? Is this here? Is it here? Or is it here? You have to try and work out where it is. So is it at the bottom, in the middle, or at the top? Look at these numbers here, look at the sign, and work out where it will be. Okay, have a moment, see if you can draw the diagram. And if you can use the number, that is even better. Just have a look and see if you can do it. Okay. What do you think? Is it going to be at the bottom, in the middle, or at the top? And I would like a reason for that, okay? So let's have a look, see who can come up with that. The camera that Fiona is using, I've got a picture of, I don't know. Okay, so see if you can draw that diagram. See if you can draw the diagram. Ah, yes, Fiona, I have a picture of a foot. It's very good. So let's have a look. Who can draw that? Who can finish that off for me? So we have methane and oxygen. Will the carbon dioxide be here, below, or above? The delta H is minus or negative 890. Will it be down, up, or the same level? Fiona, what's that? Diagram. Show me that one again, please. Really good. Excellent. That's very good. I don't know if other, let me just pin your, hang on, let me just pin your, hang on, wrong thing. I don't know if everybody else can see this. Who is this, please? Put your name on it, because this is worth, this is worth remarking. It's very, very good indeed. And show us the diagram again, please. Well done, Samo. Look at it, everybody. Just, oh, hang on, don't move it. Don't move it. It's great. Okay, there it is. We've got the carbon dioxide and the water down at the bottom, and he's got the activation energy. The question is, where is the 890? That's very good. Well done. Thank you very much. Very good. Okay. So let's go back. Okay, I'm going to just share my diagram and let's have another look at it. So here we are. So the question was, where will the carbon dioxide and water be? And the carbon dioxide and water answer was down here, and this is correct, down here, because the negative, which for some reason I can't write on, the negative is means that it is exothermic. Because it is exothermic, what this tells us, oh, hello, what is happening here? What this tells us is that it is below, it is given out. Then what we have to do is we just draw, I'm going to make this quite thick. So we start here and we go up. It doesn't matter how high you go. And we come down, and then we have to draw a line under here. And absolutely right, this is the activation energy. Now we have no way of knowing what value that is. But what is next is what happens with the 890. And this is the point, that the difference between this level, come on, sorry, my pen is being stupid today, between here and here, that level here, that is the 890. So this between here and here, whoops, sorry, there, this here is 890. So let us say this is 0, then this would be minus 890 down here. Okay, or if this was 1,000, then this would be 890 less. In other words, 120 down here. So this we would label negative 890 kilojoules per mole. Oops, sorry, I've written it in a different way that we, there, like this. Okay, so that's the diagram. And that's all you have to do with these diagrams. Sometimes they ask you to label them, and there are plenty of examples where they ask you to label that sort of diagram. I have sent to your supervisors some questions, and one of them is exactly about that. So let us look at that reaction in a little bit more detail, and then we will see where this goes into exothermic and endothermic and bond energies, because they are really important idea. Here we go. So I'm going to share my screen, and I'm going to try and explain what is happening in terms of this reaction. If you remember at the top, when we started talking about this, I said, come on, wake up. Okay. I said that we would be looking at two things. And the two things we're looking at is this here and this here. So far, what we have done so far is we have looked at exothermic, endothermic, delta H, and energy profile. Now we are going to look at bond energies, okay? And so I'm going to go down to the bottom down here, and I'm going to explain. So I'm going to look at this reaction. So here is our energy profile. And now I'm going to look at what is happening in the reaction. So when I draw CH4, some of you may not like organic chemistry very much, but this is what is happening in this. This is methane. And when it reacts with oxygen, we have two oxygens like this, and they break, and then they reform, and they make carbon dioxide. Don't worry if you do not know that this is the bonding in water and carbon dioxide, because you can do it without worrying about that. So in our energy profile diagram, I'm going to make it short and flat now. So time is along the bottom here, energy is up the side, and this is the CO2. Don't worry about drawing this bit. It's the diagram at the top that you want. It's this that you're going to be looking at. So here, whoops, sorry, not CO2, idiot. Sorry. This is oh Lord, come on. CH4 plus 2O2, and we know this CO2 and 2 waters is lower down. CO2 and 2H2O. What is in between these two? Well, when they crash into each other, they break completely. So in the middle, we have pieces, all the atoms broken into separate atoms. So in other words, we have these on the left-hand side, which we call the reactant molecules. And these are called the product molecules. But in the middle are the intermediate, the bit in the middle. And this is atoms. Sometimes it's not atoms, but sometimes it's bits of molecules, but it is broken. Okay, so they are all separate, and then they reform. So from the reactant molecules to the product molecules, we go up to produce those, and then we come down. Okay, so this is this bit here going up, the energy of activation. This is breaking the molecules. And going down the other side is making molecules, new molecules. So we are breaking, then we are making. And this is a very important idea, that when we have a reaction that goes on, we have breaking first, then making. We break the molecules, then we make new ones. Okay, so breaking, then making. It's a very important idea. Now I'm going to tell you what each one of these bonds is worth. This bond here is worth 412 kilojoules. This bond here is worth 498 kilojoules. This bond here is a very strong bond. This one is worth 743. And the hydrogen to oxygen ones are worth 464 each. Okay, so the carbon to hydrogen ones are worth 412, and the oxygen ones are worth 498. Now I'm going to just try to show you how this calculation works. So I'm just going to get rid of my graph underneath, and we're going to see what is happening. So what I have to do first is I have to break the bonds on the left-hand side, okay? Okay, so let's see if we can see what's happening. All right.
Sir,
Yes?
may you repeat for me how you calculate the number of monomer of carbon?
The number for carbon to hydrogen is 4112.
How do we calculate the number of monomer of carbon?
How do you what, sorry?
How do you calculate the number of monomer of a
Okay,
carbon?
you are given this in the question. You do not have to remember it. Okay, so in a question, I will show you a question, or your supervisor has a question. But in the question, it will tell you that this is, whoops, sorry, oh, I'm rubbing it out. This is, I will rub it out completely. That this number here is 412, okay? So they tell you that in the question. They tell you this one is 412, the oxygen is 498, and so on, okay? So they tell you that to start with. Now, if you remember that we have to break the reactant molecules, then how much will that be? Well, it will be like this. I have to break 1, 2, 3, 4 times carbon hydrogens. I've also got to break 2 times oxygen. And then I'm going to make new 2 times carbon double bond oxygen, and I'm going to make 1, 2, 3, 4 times H to O. Do you see what I'm doing? What I'm doing is I'm saying, okay, so I'm going to break 1, 2, 3, 4 of those. Okay, so that would be 4 times 412, because each one of them is worth 412. Then I'm going to also break, I'll change the color so you can see where it's coming from. I'm going to break these. So I'm going to break 2 times 498. That is how much it is going to cost me to break those. Then I'm going to make some new bonds. So now I've got it all smashed up. Now I'm going to make some new bonds. I'm going to make this one and this one. So that is 2 times, each one is 743. And I'm also going to make these 1, 2, 3, 4, So I'm going to make 4 new bonds, and each one of those bonds is worth 464. Okay. So in other words, I have to break the ones on the left and make the ones on the right. So what I'd like you to do is somebody to do the calculation for me to tell me how much there is on this side and how much there is on this side, and then we will be able to do something. So I want you to add these ones up and add these ones up, and then we will work out what this tells us. Okay, so just see if you can work out what that is, and we will then be able to move on from there. Okay, let's see if anybody's got the answers so far. So has anybody got the answers for those? Excuse me. Breaking 2644, making 3342. Excellent. Well done. Very, very good indeed. Well done. That's very, very fast. Well done. I'm very pleased. Okay. All right. So we've had one answer, which is 2644. Well done. Really cool. Nice mask. Excellent health as well. And 3342. Okay. 2644 and 3342. Now, this is where it gets to make sense, because we've nearly finished. Okay, we've nearly finished. I just want to share this idea with you. So now I'm going to go back to my diagram. So our answers are, this is 2644 and this is 3342 according to our genius. Now let us look at our diagram again. So I'm going to leave those numbers just at the top of the screen. So here is my diagram. So my diagram is energy up the side, and I know I start with CH4 and 2O2. And I know that lower down, I have CO2 and 2H2O. And I know it's energy up the side, time along the bottom. Hello? Okay. If we say this is 0 here, then from here up to the top of here is 2644. In other words, from here, whoops, sorry, that's gone way too small. Come on, get big again. Smaller than that. Okay. From here up to there, up to the top of this energy of activation is 2644. And then from here down, it is going to be this number here, 3342. In other words, breaking bonds, breaking them as we have to put energy in. So this is energy in to break bonds, and this is energy out to make bonds. So we go up 2644 and we come down 3342. In other words, the total is 2644, which we have to put in, and then we get out 3342. 642. And that equals negative 698 kilojoules per mole. This is the answer to this one here. It is 698, the difference between going up and then going down. So in other words, this bit here is endothermic, and this bit here is exothermic. And the exothermic and the endothermic end up, depending on the size of these two numbers, gives us, in this case, an I picked the wrong color there, doesn't matter. I picked the wrong color, but it is negative 698, which is this arrow here, negative 698. Okay, so I think that may be quite hard for a start, but hopefully it will start you thinking and you will start to make a little bit of sense of it. I have linked, I have recorded this, and what I'm going to do now is I'm going to put it into YouTube, and then I will send your supervisors that. But your supervisors also have 3 questions, one of which is quite easy, and the other 2 we have now dealt with. At the beginning of next lesson, what we will do is we will go through the answers and explain them, and then we will move on with the next bit. Next week, I will be back in the laboratory. Today I'm at home. I will be back in the laboratory and I will show you some exothermic and some endothermic reactions, some which take in heat, endothermic, some which give out heat, exothermic. Okay, so we will do those. But now you have been very patient, and thank you very much for being here. If you have any questions you want to ask, just wait. When everybody else goes, that will be fine, and we will just we will just go through them. Okay, but that's the end of this lesson. So Silver Spring, and I think you've actually just gone, Glory, but and Genesis, thank you very much indeed for being here. Next time we will pick this up, we will go on further with it. I hope for many of you that was okay. Don't worry if it wasn't. If you want to wait and go through it again, we will do that now. Okay? Dan, you're looking good.
Thank you. Thank you. Good to see you.
It's nice to see you. Very nice to see you. So, thank you. Thank you, Vienna. Cheers, guys. Thank you very much. And if you want to stay, if Silver Spring last time, thank you very much. Bye-bye. If you want to hang on and ask a question, we will do it. If it's all okay, just go. And it's been very nice. Yes, and your daughter hasn't turned up.
Thank you, Teacher Mark.
It's a pleasure. Next week we will have Juju.
We're looking forward to it.
Okay. See you later, Sophia. I will send the YouTube link. See you.
All right.
Thanks, mate. Cheers. Cheers, Dan. Have a good evening.
Good evening.
Good
You
evening.
too. Thank you.
Cheers now.
Fatma has a question.
Fatma always has a question. I will tell you the answer, Fatma, is to be happy, and everybody will love you, and that's it.
Fiona, how did it go with your team?
Oh, she's gone.
Oh, Fiona has disappeared.
Oh dear. Oh well. How was it with yours, with Glory, Dan?
Is Fiona at Glory?
Oh, was it? Were you at Silver Spring? Sorry.
Today I was at Independent Point.
Oh, I didn't know it.
I
It's your
was,
own school.
I was participating to learn.
Ah,
Yes,
well,
I was my own student.
I think it's good. Independent. I like the idea of having an independent point. It's really good. How are you, Dan? Are you good?
I'm doing well. I'm doing good. Thank God.
Good. Excellent. Yes,
It's
thank
been
God.
it's been a week of resting and restructuring.
Oh, okay. And how's it been inside your? How are you inside yourself? Are you a happy man? You always seem happy to me.
Yeah, yeah. I would say that I get satisfaction from what I do, especially interacting with young people and just trying to guide them and share hope with them. So
I think
it's
honestly,
it's a joy enough. It's a joy enough.
I tell you what, Dan, I think you do a great job. I really do. Honestly, I think you do a fantastic job. It's also true of all the other supervisors,
Thank
but
you.
you are unremittingly cheerful. Apparently, at least you do a good job in lying about being cheerful. You always look cheerful.
Yeah, and that's my nature. That's my nature. You know, these young people.